mention few, he was invited in the International Congress of Mathematicians in Rio, 2018. Gave talks there, and he won a few prizes. I encourage you to give a look to his webpage. But now let's jump to the talk, and the talk is exactly the connection between dynamical system and Markov chains. Carlangelo?
Okay, so thanks a lot for having me. And yeah, I mean, actually, to be completely honest, I mean, I'm born as a physicist, so I don't know, maybe I'm not a mathematician, nor a dynamical system, nor a probabilist. I don't really know what it is, but it is true that my work, I mean, somewhat has some kind of element both in dynamical system and in probability. And since this is kind of a probability seminar, I wanted just, instead of trying to tell you what is the last result of something, I wanted to do something a little bit more very basic, somewhat, just in case people are not aware of this connection. And I want to show to you that indeed a dynamical system can be essentially seen in a profitable way as Markov chain. So let me just get to the point. So a dynamical system, it is just they are both in continuous time, like a space and a map. I mean, a measurable space. I mean, a measurable space and a measurable map, or it could be a flow. So it is either the action of N or Z or R or something like that, or it can even be more general if you want, like action of group or whatever. But for simplicity, let me just discuss discrete time. So, I mean, it's just the action actually of N, of the natural number on X. So the point, what it is the situation? The situation is that if you have the initial condition X naught, then the evolution is determined essentially by this rule. So given the initial condition, you apply the map at power N, and then you get the state of the system at time N. And of course, this is kind of, okay, there is no probability here, but if you assume that you don't know exactly the initial condition X naught, so the initial condition is distributed according to some measure, which may represent several things. It could be either that you have several copies of your system and each system is in a different initial condition, or it can be a representation of your ignorance of the initial condition, whatever. It can have several interpretations, but nevertheless, you consider the initial condition a random variable, and then the expectation is simply given by the average with respect to this measured mu. And then, if you do that, then of course xn is a random variable, and xn is just a Markov chain. It is a very degenerate Markov chain, but it is a Markov chain. The probability element is only in the initial condition. So from this point of view, you can see dynamical system as a subset of the theory of Markov chain. And on the other hand, I mean, if you take a Markov chain, you can look in path space, and then you have that the shift in time, it is just now a dynamical system. So in some sense, the two things have many things. A big part of probability can be seen as dynamical system. A big part of dynamical system can be seen as probability. I mean, I don't see much of a difference with these two things, but this is kind of just an abstract mathematical thing that many times you can say, okay, this thing I can recast it in a different language, but the point is that profitable to do so or not? And my point of view, and what I wanted to try to show to you, that indeed to view dynamical system as Markov chain is profitable because you can essentially try to copy many ideas from the theory of Markov chain and try to get a corresponding result in the field of dynamical systems. So that is essentially the argument of the talk. And let me just go to some concrete, more concrete stuff. So you see, a different way of seeing is that if you have an observable G and you want to see the expectation of this observable at time n, then of course it's given by this formula. But then you can also this formula can also be seen as the push forward of the initial measure by the map at time n. So probably is the pullback. I have no idea. I never understood the difference between the push forward and the pullback. It's a star that is above or below. I don't know. Whatever. But anyhow, this is the formula. and so this F star essentially is like the transition operator of the Markov chain, because it just tells you how the measure evolves. So if you are so general, then you cannot really say much. But let's consider some very simple case just to tell you what this point of view can lead to. And so I will consider the simplest possible case, but much more general cases can be treated with the same type of ideas, only the thing gets much more technical. So I don't think I want to become too technical, and so it is just about broad ideas. So the simplest possible case is the case in which mu is absolutely continuous with respect to this. If X is a Riemannian manifold, then so the space is a Riemannian manifold, then mu is absolutely continuous with respect to the Riemannian volume. And also, I will consider a case in which F is a smooth expanding map. So it's C2, and the derivative, the inverse of the derivative is strictly smaller than 1, meaning that if you have two nearby points in the image, they are farther away. Okay, so this is, of course, this cannot be an invertible map, because if you are on a compact manifold and you expand, then the image must cover the manifold more than once. But nevertheless, it's essentially the simplest example of non-trivial dynamical system if you want to study this type of ideas. Okay, so we are in this setting, and let's see what we can do in this setting. So the idea is that you want to, so let me just do a computation for you, so you can go away from this seminar just saying, okay, at least I saw one computation. So as I said already, F is not invertible, so it has a partition of invertibility. That means that there are element pi such that F of pi is all the space, and it has inverse branches that I call phi I. So this is just, I take, let me just do a picture, let's say that it's just a two-dimensional picture, something like this, for example. So this is an expanding map, this is one, and then this will be P1, this will be P2, and the image is 0, 1, and the inverse map phi I is essentially this map here, that phi 1, that goes from here to here. Okay. That is. So you can just use this inverse map. You just write, this is the quantity you want to compute. I didn't want to do that. This is the quantity you want to compute. Then you can write it in this way, because this is just phi compose F, and phi I compose F is just the identity by definition. And then you just change variable. This is a basic change of variable. So you just have the determinant in the denominator. That's what happens when you change variable. And then you get that you can write the expectation of the variable of a function phi of the variable, random variable x1, so at time 1, in this way. So, and this guy, this is the new density. So this is the new measure, and this is the new density. So you have that in this particular case, if you have a measure that is absolutely continuous with respect to the Riemannian volume, the push forward will be absolutely continuous with respect to the Riemannian volume, and this operator L, which is called the transfer operator or the well transfer operator or whatever, it has bazillion of names, but essentially it's a transfer operator, will have this form here. That is the form that you get from this. Meaning, well, this is Y in the pre-images, because here you have as many pre-images as inverse prime. So this is a more convenient way of writing this formula here, which defines the operator LH. So in some sense, you can, in this way, LH now is really the transition. It's exactly like the transition matrix of a Markov chain, just only taxon density, and that's it. It's, of course, it is a Markov chain with countably many states, but okay. All right, so as you do in Markov chain, what do you want to study? You want to study essentially the spectral property of the transfer of the transition matrices. So here, by analogy, you want to study the spectral property of the operator L. That is what you want to do. And if you understand the spectral property of the operator L, then you can say things like, what are the long-time behavior of this process, of this dynamical system, if it has, which invariant measure it has, and so on and so forth. But you see, there is a basic difference here. Well, maybe I say it in the following one. Yeah, so on the other hand, yes, if you want to look at what happened at time n, then you do this argument n type, and you end up with the power of the transfer operator, exactly as a Markov chain. And of course, if you have a density that is invariant with respect to the transfer operator, this is an absolutely continuous invariant measure. Okay, so, but that's fine. But you have always to remember that dynamical system has a basic difference with usual Markov chains. The Markov chain, they don't have typically, of course you can make counterexample, but this is a Markov chain after all, but typically they don't have that many invariant measures. On the other hand, the dynamical system typically have a lot of invariant measures. Not counterexample, there are dynamical systems with only one invariant measure. They are called uniquely ergodic, but they are very rare. Typically, there are a lot of invariant measures. Also because, for example, orbit, then you can put on each point of this periodic orbit a delta mass, and this will give you an invariant measure because the dynamic will just simply go around the periodic orbit.
Can I interrupt you on this?
Yes, of course.
Because because it might help to understand what you mean for invariant measure for Markov chain. If you have two of them, distinct two, any linear combination would be an invariant measure. So you would have an uncountable.
That is correct. That is correct. But I mean ergodic. Yes. Invariant measures, they are they form some kind of convex set, and then they have extremal points. So I'm talking about.
I see what you mean.
So yeah, because otherwise, each time that you have two, you have infinitely many, right? This is not what I'm talking about. Here, if you have a lot of periodic orbit, each measure on, like if you have a periodic orbit, let's say that you have a periodic orbit that has just 2 points, okay? Then the dynamic is like this, okay? And if you put a delta mass 1/2 here and the delta mass 1/2 here, just visit everything. So, and so it has nothing to do with another periodic orbit, which maybe it has, period 3, and you have 1/3, 1/3, and 1/3, that's the mass. This is completely different periodic orbit. It has nothing to do with convex combination. And since typically dynamical is a lot of periodic orbit, then this already gives you a lot of invariant measures. But you can construct many, many more. For example, you can take some set and look at all the trajectories that never enter this set. This is an invariant set, and on that you can construct by the strategy of Krylov-Bogolyubov an invariant measure, and this will be an invariant measure supported on trajectory that never enter in a certain subset. Since the subset that you choose is arbitrary, then you have a lot of possibilities. So typically, there are really a lot of invariant measures. However, if in the case that I'm discussing, if you discuss invariant measures that are absolutely continuous with respect to the Riemannian volume, we will see that they cannot be that many. In fact, there is only one in this, but we will see it shortly. Okay, so that is for invariant measure. And now I want to study this transfer operator. Okay, the first thing that I study is that if you look at the integral of LH, then you get that this you can write it as LH times 1 is the same. And then you can, by the definition of the transfer operator, this is H1 compose F, which is this thing. And then 1 compose F is 1, and so you get this. Okay, and this means that is exactly what happened with the transition metric of a Markov chain, is exactly the same. The consequence is that the L1 norm is not increased. Okay, so this is okay, fine. This just says that if you are a probability measure, it remains a probability measure under push forward. It would be idiotic if this were not so. But okay, it doesn't tell you much, right? It's essentially nothing. Just probability measure goes in probability measure. If you want to understand better, you have to understand something about the property of the operator L. And it turned out that it's a good idea to look at the derivative. Okay, so if you look at the derivative, it's a computation. I mean, you don't really need to look at it very much, but essentially you derive with respect to a variable. And then what do you get? You get the derivative of h with respect to its own variable, and then since y is the inverse, you have to take the derivative of y with respect to x, and then you get this stuff here, the derivative of the inverse matrix. And then, of course, you have to take the derivative of this guy, which is this guy over here. So you get one term that has the derivative on h, and one term that has no derivative on h. Okay, fine. But then if you take the L1 norm, this is the gradient of LH. And this guy is strictly smaller than lambda minus 1, where lambda is bigger than 1. Just this is the assumption, right? The assumption was that dyf minus 1 was smaller than lambda minus 1, smaller than 1. This just means that the map is expanding. So that means that you get something smaller than 1 here, and here you just get this stuff here is just something bounded because the map is C2, so here there is the second derivative here. So it's bounded by some constant, and then you have the L1 norm of H. So this is a key inequality in this game. It's called Debril-Forté, because that the first time it appeared in probability, and then, so this is where it appeared in probability, and this is appeared in dynamical system in the work of Lazotte and York. Exactly on expanding map, indeed. So this inequality essentially tells you that the operator L has some smoothing property, because if you start with an H that has a very high derivative, you can start with an H that has some, very high derivative, and then you integrate it. And you push forward it. Then the derivative decreases up to a point, right? Because if this is the probability measure, then this is 1, and then this is b, and then it means that this will decrease until you get to some situation which is kind of, more smooth. But then when you are smooth enough of the order of b, then this decrease, but then you add b, and so essentially at a certain point, the nonlinearity of if the map is linear, then b is 0 because the second derivative is 0. Then you really converge to something that is that has zero derivative to a constant. But if the map is nonlinear, then this is something. So this measures essentially the nonlinearity of the map. In fact, this quantity here is called distortion. And the distortion is exactly something that measures the nonlinearity of the map. So this B here measures more or less the nonlinearity of the map, and it tells you that your measure will get more regular up to a point, essentially, okay? So this is very far away for the situation, for example, in which you can consider a stochastic differential equation. Because in a stochastic differential equation, if you want to see how the measure evolve, then essentially you convolve with the Gaussian, which means that no matter how bad it was the initial condition, it immediately becomes infinity. This is not the case here. If the measure at the beginning is only C1, it will never become C2. I mean, there's no reason why it should become C2, but the C1 norm will decrease. Okay, so that is some weak form of and this means, sorry, I mean, that's just, now there is some abstract theory that I don't want to enter in it, but is a theorem essentially due to many people. The form that typically people use now is due to Hellion, which says that this inequality here, plus the fact that, so you see what space I have here. This is the norm of L1, and then this is the norm of W11, the Sobolev space in which you control the L1 norm of the function and the L1 norm of the derivative. And of course, if you take the unit ball of W11, this is compact in L1. Okay, so this compactness fact plus this inequality is sufficient to say, by some abstract theorem, that the spectrum of L in W11 looks like this. There is a point here. This is the invariant measure, must exist by Klirov-Bogolyubov, essentially because you have compactness, right? So you can redo Klirov-Bogolyubov. Instead of using weak compactness of measure, you can use the compactness of W11 in L1. So you start with the function W11, you take the average, and this will converge somewhere by compactness, and this will be an invariant measure. So there is such an invariant measure. Then there is something that is of radius lambda minus 1. This is essential spectrum, but this is a bound for the essential spectrum. And outside this disk, there can be only finitely many eigenvalue of finite multiplicity. Possibly they could be also there, but you can make an argument, a separate argument showing that there is nothing on the unit circle. And that means, there is nothing on the unit circle, and that means that the operator L, so you have some eigenvalue, and the operator L has a spectral gap. Okay? That means that if you look at Ln, this will look like if you apply it to phi, then it will look like the integral of phi time the invariant measure plus order of mu to the n, when mu to the n is the gap, the spectral gap between 1 and the second highest eigenvalue. Okay, so it means that you converge exponentially fast to the invariant measure, which is okay. It's like if you have a Markov chain and the Markov chain is aperiodic, then you converge exponentially fast to the invariant measure. So okay, fine. And but that's not all what you can do. You can say, okay, fine. So there is only one invariant measure. It is absolutely continuous with respect to the Riemannian volume. Very nice. It is also C1. I mean, here I just proved that it's in W11, but you can, with a little bit more effort, you can prove that it's C1 if the map is C2. And if the map is CR, then it is CR minus 1. Maybe you can do a little bit better, but more or less that's what you can do. And then, okay, fine. What else can you say? Well, a very important quantity in dynamical system and also in probability is this one. This is the Birkhoff average. I mean, you just take an observable, you look at G of xk, and then you take the average. And of course, by Markov theorem, or if you are in probabilistic, by the law of large number, which is essentially the same, you get that the limit for n going to infinity is the average with respect to the invariant measure, almost surely. This is almost surely, it means h x dx, almost surely. This is the probability measure I'm referring to. Okay, fine. And then you can ask, okay, fine, but what about this type of quantity? I want to know what is the probability that this average, this sum is not its limit, so differable from its limit by some alpha. So this is what is called the large deviation. I would like to study, for example, a large deviation. What is the probability? This is something that you can do in probability. Can I do it in this field of dynamical system, essentially trying to copy what has been done in probability? Okay, so what is the idea? Okay, first of all, you subtract the average. Yeah, that's not a very deep idea, but it's useful. And then for each lambda, so this lambda, I'm not sorry, this lambda has nothing to do with the expansion of the map. This is a parameter. So I use, unfortunately, there is a shortage of letters, so I use lambda for two different things. Apologies. I mean, this lambda here is just a parameter. So you want to, for example, you want to compute this probability now, so that this quantity where you subtracted the average is bigger. The limit of this is 0, right? And you want to see what is the property that is bigger than alpha. I put n on this side, but it's just, otherwise you can put a 1 over n here. It's the same. Okay, so this, I do it exactly what the people do in, for Markov chain. I say, okay, but this trick of looking, well, this is like looking at the fact that this exponent is bigger than 1. It's exactly the same. And then there is this trick that each time that I look at it, it seems kind of crazy, but it works, which you say, okay, fine, this is e to the lambda alpha n, this is this part, and this part here, instead, I just put the expectation. Of course, the expectation on this set, this is bigger than 1, okay, and then I can add the rest of the place where this is smaller than 1. So this seems to be crazy estimate, right? Because I mean, it seems I put something wildly bigger than what I have here. So I don't know. I find it always surprising that it works. My first reaction is that this is completely ridiculous. You are throwing away the baby and the mother with the water here. But nope, it works. Okay. I don't know. Some smart guy must have invented this. Okay, fine. And then you just write it in this way. Okay, now of course you want to take advantage, then lambda is arbitrary, and then you want to minimize this quantity, choose the lambda such that this is as small as possible. And this means that you have to maximize this quantity, and this means that you have to take the Legendre transform of this quantity, which is the exponential moment. So you have to study the exponential moment. But up to here is completely indistinguishable from what you would do for Markov chain, right? It's absolutely the same. Okay, fine, or for any large deviation argument. I mean, this is just the upper bound. You can do the lower bound as copying again more or less what people do in probability, but let me just discuss only the upper bound in large deviation. Okay, fine. Now, there is a trick that was originally invented by Nagaev, as far as I know, in the 50s, late 50s, for exactly Markov chain, and then it was adapted to dynamical system by Gevash and Hardy in 88. And the idea is very simple. You say, okay, I want to compute the exponential moment. Fine. Then I take the first element in this sum, and I take it out. Here it is. It's just when k is equal 0, it is just e to the lambda g hat. I mean, that's it. And then the rest, I go from 0 to n minus 2 instead of n minus 1, but is composed with f. And now I use the transfer operator. So I have this quantity here. Okay, now it's exactly what it was here, only now it goes to n minus 2. And then here I have L that is applied to H, but I have this factor. So you see, I can define this operator, which is exactly the transfer operator of the system, applied not to phi, but to phi multiplied by this exponential factor. This is called many times a twisted transfer operator. So I find it a ridiculous name, but that's what people call it. And then you say, okay, fine. So this one, it is just L lambda applied to H star. And then you see, this is exactly the same situation that you had here, only where here you had H, now you have lambda L H. Okay, but still the argument, you can do it again. And so you do it n time, and you end up with this. So you see, you have that the exponential moment is given by the power of some operator applied to, in this case, to the invariant measure. I mean, you can also start with a different measure. It doesn't make any difference, but just to make it simple, it's just applied to the invariant measure. And so if you want to see how this guy grows, you have to understand how this, what are the spectral property of this operator. So that is, I mean, this is essentially copied from Markov chains. I mean, just you have this operator with this twist, and then you can start with this guy. And since you see what you want to see is really not really this guy, but this guy divided by 1 over n, then you are looking at lambda over n. So you're looking at reasonably small lambda. That's what you're really interested in. So you can try to look at this operator for not too big lambda, but using perturbation theory. And that's what people do. So you just apply standard perturbation theory. And as I told you before, the operator at the beginning was, if lambda is equal to 0, it's just the transfer operator, then this will be 1. This will be what here is called pi 0 applied to phi, will just be H star integral of phi. There's just a rank 1 projector. And then you would have this guy, Q0, which is the remainder. This will be just a smaller to the n, which is much more than some constant, some mu to the n. So this decays exponential. And by standard perturbation theory, this property remains. Okay. So you get that this operator has this spectral decomposition. This goes to 0 exponentially fast. The only thing that this is just very close to this operator. The only thing that you need to understand is what the hell is this new eigenvalue. Okay? When I change lambda, what happened to the leading eigenvalue of this operator? And then you just compute, I mean, just exactly use the perturbation theory, and you discover that the logarithm of this guy is given by 1/2 sigma square lambda plus some remainder, where sigma square, it is just the usual thing, which is just the variance of this random variable. Okay.
Oh.
And this is the, I don't know, how is it called, this formula? This is just the dissipation formula. Yeah, someone wanted to ask something?
Oh, yes.
Yeah.
It's me. I thought you were going to the Perron-Frobenius directly in the previous slide, but you took me off guard when you are considering lambda small. You think lambda small would be optimal there, or because...
No, but the point is that what is the quantity that I want to study? The quantity that I want to study is this quantity divided by 1 over n. This bigger than not 1 over n. So in reality, what you really, I mean, it is enough to control lambda relatively small in order to get large deviation. But I will show you in a second. I mean, it's just, yeah.
Okay.
Yeah, I mean, in principle, I mean, it depends. I mean, it depends. If you want to control all the rate function, then you have to consider all lambda, okay? But if you want to consider the rate function for deviations that are not so large, then it is enough to consider small lambda. I mean, the function is but I mean, if you want to, it's smooth. that means that it has a maximum. That means that this sum here cannot be bigger than n times the maximum. So the rate function must be very strange. At a certain point must go to infinity, right? Because the probability of having a deviation that is bigger than what at most the sum can be is zero. So if you want to really look at very large deviation, that is a bit complicated. But let me just.
That I understand. The deviation. The rate function would be infinity is pretty clear after a threshold, but doesn't suggest that the lambda is small, close to zero, though. But the optimal lambda. But I'll wait for the next.
Okay. Wait for. Okay, fine. Here we are. And so this is the usual formula for sigma square. Okay, fine. And you can prove that, of course, you have this problem that it could be zero, right? But you can prove that this is zero only if G has this form for some continuous map. So it's a continuous coboundary. And this is not so difficult to check, because if you take a periodic orbit, then you can look at this quantity along a periodic orbit must be zero, because it's just a coboundary. Right? If you sum this along a periodic orbit, this sum and this sum is the same, because this is just sum along the periodic orbit only shifted by one. And so it's just enough to find one periodic orbit on which this function has not zero average, and then you know that it's not a coboundary. You know that this is not zero. Okay, so there are a lot of obstruction. Actually, if you have countably many periodic orbit, you have countably many obstruction for a function be a coboundary. So it's pretty rare. Typically, you have that this is not zero, even though you can clearly create a example. Right? You check a phi, you construct this function. Something. Typically, this is not going to happen. Okay, and now we have this situation. Okay, now I have to look at this stuff. This is the quantity that appear. Where is it? This is the quantity that appear in my exponent. So this is the one I want to do the Legendre transform of. So okay, let's compute. The logarithm of this and this is actually the logarithm of the maximal value. Okay, now I know what the maximal eigenvalue is. I compute the center transform of this guy. You can compute what it is, and it happens when lambda is it is something like alpha over sigma square, something like that. I mean, this is the maximum of it is lambda alpha minus sigma square over 2 lambda square. So you can compute easily this guy, what it looks like. It looks something like this, and this one should be alpha over sigma square. So it's not so big if alpha is not super big, right? Alpha is your deviation. So so typically for reasonable alpha, you get this formula here. This is the typical large deviation formula. I don't know if this answers your question. This is the optimal lambda that you choose when you do the.
It answered my question. Yes. Thanks.
Okay, good. So, yeah. Also, you see, I mean, in fact, I always consider lambda positive. So you can say, but when you do the Legendre transform, you also consider lambda negative. Yeah, it's true, but this guy is positive. So if you put the negative, it doesn't change. Okay, so, and this is the last deviation estimate that you get. Very good. On the other hand, you can do the same if you want to consider the central limit theorem. If you want to consider the central limit theory, instead of having lambda, you have I lambda, you put a complex, and then you get again a transfer operator, only now the twist, you multiply not by e to the lambda, but you multiply by e to the lambda g, okay? And then you have to divide by 1 over square root of n, and you get this formula, essentially by the same argument. And this one, of course, is the characteristic function of a Gaussian, apart with an error. And then you get this quantity is close to a Gaussian. And actually, this is a rather powerful method, because if you just put your hand in it, you can get pretty good estimate of what this error is. And you can even do an edgeward expansion if you want. So you can really push it very far. Okay. So it means that this allows you to get a very, very good understanding of what this average for dynamical systems look like, with their statistical properties and so on and so forth. Okay, so that's more or less what I want to tell you on this situation. It has been kind of, a lot of people have been interested in non-stationary case. Non-stationary case is like this was an homogeneous Markov chain. Now we want to see a non-homogeneous Markov chain in time, right? So it means that as time goes on, the transition matrix changes. And what does it correspond in the dynamical system? It means that I don't have one map, but I have a sequence of map, and I have a sequence of observable, and then the random variable xn, it is given by fn minus 1, compose fn minus 2, compose f 1, 0, 1. No, ft, I start from 0, I'm sorry, I don't know what that is. And then this will be gn. Okay. So this is, each time I change the observable, and then the dynamics evolve in this way. So you get this function here, composed gn. Actually, it's the other way around, right? I'm sorry. Gn composed. It was written below. I'm sorry. Exactly what is written here. And now this, I want to understand this random variable here. What can I do? Well, you can do exactly the same trick as before. The only problem is now these operators now are all different. They are not all the same. And this is a little bit annoying, because now you cannot do now this is the equivalent of multiplying matrices, which are all different. So you cannot use spectral theory, right? Because you don't have the power of some matrix. So you need a different idea. So there are many ideas that you can take example. They can try to copy. In general, it's very hard. In general, it's very hard, because if you, even for matrices, if you gave me a bunch of matrices, you ask me how the product is growing. What the hell do I know? Maybe, you can put one matrix is inverse, one matrix is inverse, another matrix is inverse, and then you get one at the end, right? So you can get anything. It's completely nonsensical problem. I mean, it's too general. But there are situations in which you can say something. For example, if the matrices have a common cone that they preserve, typical example, you have that the matrix send the vector with positive entry into vector with positive entry, then you expect the product to grow exponentially. It's just a generalization of Perron-Frobenius theory. So this is the idea that I would like to push. And this is an idea that it can be formalized in a very effective way using projective cones. So a cone is just a cone is just a cone. A cone is a set that if you take an element and you multiply by some positive real number, then this the element that you get is still inside the cone. And I take a positive real number because I want cone, such that if I take the cone and that I take minus the cone, so minus the element, there is no intersection. So this is half cone, so something like this, where there is no zero. Okay, so this is such cone C, for example. Okay. So the very interesting thing is that if you have such a cone, and in general, it actually must be convex. So in higher dimension must be something like this. If you cut it with a transversal plane, then you have to get a convex set here. So that's what it means, a convex cone. The sections are convex. And of course, if you change the section, it always remains convex. Right? You cannot change convexity, just changing the way in which you cut it. So it's a property of the cone, not of the section with which you cut it. And you can define an order relation. And the order relation is simply given by f is smaller than g if g minus s belongs to the cone union theorem. And this gives you a lattice. If this belongs to a vector space, now you have an order relation in this vector space. You can check that it behaves well with respect to the sum, with respect to the product by a scalar, and so you get a lattice. And moreover, in this lattice, if the operator L sends the cone inside itself, this is like saying that if you have a positive element in the lattice, LG is a positive element in the lattice. So it means that suddenly this theory of operator that preserve cone is absolutely equivalent to positive operator in a lattice, for which there is some theory actually. So that is the, and there is a very powerful idea, goes back, but indeed is formalized by Hilbert, that you can construct an Hilbert metric. Essentially, I mean, here is a formula, but let me just tell you what it is. This is the section of the cone, okay? You take 2 points, x and y. These are rays, right? You take subtract cross product, which is x minus v, y minus u, divided x minus u, y minus v. You take the logarithm, you take the absolute value, and this is the distance between x and v. Since the cross product is invariant with respect to projection, it means that no matter how you cut the cone, this quantity here is always the same, and the logarithm of this quantity is always the same. So this is really the product, a distance between the ray that goes through the point x and the ray that goes to the point y. So it's a projective metric. And of course, in this metric, this guy is it has an infinite diameter. And for example, if you are on the complex plane and you take a disk, this Hilbert metric is nothing else than the Poincaré metric. And if you take an half plane, then you get the Minkowski, whatever. I mean, the usual hyperbolic metric in the half plane. So this is very much connected to hyperbolic geometry, and this kind of, I mean, it's kind of a special case, like of things like Kobayashi metric and stuff like that. But it's kind of surprising if you look at it in this formula here, that is a metric with this locker in here. You can say, well, it's bizarre, but this turned out to be a metric. I mean, Hilbert was a smart guy. Okay, so this is some algebraic formulation. This is a geometric formulation. Okay, and then there is a theorem due to Gareth Birkhoff. So this is not George, this is the son. And the theorem says essentially that, you see, imagine that these metrics are, imagine the case of positive matrices. Okay, so you take a positive matrices, that is a matrix with all positive elements, and then you take the image, and you get the vector with all positive elements. But if you take a vector that has some zero element, it could be that the image has still some zero element, so it's on the boundary of the cone. So the boundary of the cone could go on the boundary of the cone. And then you don't have that you can apply Perron-Frobenius theorem. I mean, you can apply Perron-Frobenius theorem is the map if the cone goes strictly inside. So you have to, then means that if you take a vector that is non-negative element, the image is all strictly positive element. But this is not so clear in infinite dimension. What does it mean that the boundary doesn't go to the boundary in infinite dimension? So the idea is that you say, okay, I look at the image, okay, I'm sorry, this T should not be a T, this is an L, okay. I take the cone, and I take the image of the cone, and then I look at the diameter of the image. So I take the Hilbert metric in the image and I compute its diameter. If this is finite, then it means that things is going strictly inside because the diameter of the cone is infinity. So if the diameter of the image of the cone, you have a cone here, then you have a cone here, and then you have the map L. Okay, and if the image is something like that, if it is finite, if the diameter of the image, so this is not get to the boundary, you don't touch the boundary, because the boundary is at infinity. Okay, so if this is finite, this means that you are strictly invariant, and there is this amazing formula here that tells you that the distance in the Hilbert metric between the images is the original distance multiplied by the hyperbolic tangent of the diameter over 4. And since the hyperbolic tangent is always smaller than 1, you get contraction in the Hilbert metric. Fine, you get contraction in the Hilbert metric. Oops, I am going over time. Let me try to finish in 2 minutes then. So let's do the super simple case, matrices with positive element, bigger than some A and all smaller than some capital A. And of course, they are Markov matrices. So the L1 norm is conserved. I mean, the sum of the row is 1. And then you take the cone given by vectors that are all positive entry. Then you can compute the Hilbert metric. It's given by this formula. It's just this ratio, and you take the sup. And then you can compute the diameter of the image, which is given by this formula here. So it just depends on the ratio of this A and this small a. It's twice the locally. Okay, so this is finite. So you can apply Birkhoff theorem. If I apply Birkhoff theorem, you get that the contraction is given by this quantity, which is smaller than 1. Very well. And then if you take 2 vectors, you can compute that the distance in the infinite norm is given by the infinite norm of y, if y is the biggest, otherwise you have the sup between the two. And then you have e to the theta, the original distance minus 1. Okay, so that means that the Hilbert metric can control a more natural distance, right? Because you say, okay, these are close in the Hilbert metric. What do I care? I have no idea what Hilbert metric really means. I would like to control the L1 distance or the L infinity distance. So here, just show that the Hilbert metric can control the infinite distance, L infinity distance. And then you want to consider this product of matrices. Okay, so you do this product of matrices, and this is equal to n is the dimension of the space, and then you get, if this have both L infinity norm 1, then, for example, or you can do the same with L1 norm 1, which would be more natural, then there would be probability, but I was late here when I wrote this. Anyhow, it's just some constant, because in finite dimension, all the norms are equivalent, so it doesn't really. So here there is some constant that depend on n, and then you get this stuff here. But by Birkhoff theorem, this each time contracts by n, by nu, sorry. And so you can contract n minus 1 times, and then the last piece is this one, and this is finite, and so you get twice the diameter of the image. And so this means that here there is some estimate that shows that these two guys go exponentially to 0, the difference. It means that it doesn't matter what was the original vector, they all converge. They don't converge anywhere here in general, right? Because these guys keep changing, but their difference converges to 0 very fast. So it doesn't, so this is a loss of memory. It doesn't matter from where you start, you can infer that you will forget the initial distribution, because what happens just depends from asymptotically depend from this matrix, and the loss of memory is exponential. So this is what happened in this very simple case of Markov chain. And if you want to apply to a dynamical system, well, you just use this Lasota-York inequality, to get, where is it? Here, you just get this cone. You see, you get functions that are positive, and you have the derivative divided by the function is bounded. That means, in other words, that the logarithm of h prime is bounded by a. So the logarithm is the derivative of the logarithm is bounded. This is the cone, and then you do essentially what you did before. You have to compute the diameter. So this cone is invariant if a is large enough. This comes again from the Rasota-York inequality. And then you have an invariant cone, and you can compute the image. The image has this formula, the diameter of the image. And then you have Birkhoff theorem that it tells you that thing goes exactly as for matrices. You just copied from matrix whatever, and then finally you get, this is just, for example, the L1 norm, and you get the same that you can control with the Hilbert metric. You can control a reasonable norm. And I'm just going very fast because I am out of time, but just to give you the idea. And then you get exactly as before, that the C0 norm of this difference goes to zero exponentially fast. So again, you have loss of memory, and there is another case in which you can happily copy what people can do for finite state Markov chain, and you can mimic it and do it for dynamical system. Well, I stop here. I'm sorry, I went over time.
We interrupted you many times, so it's. But please join me in thanking Carlangelo for the wonderful talk, and please, is there any question that you would like to address? We have time for a few questions.
I have one question.
Yes.
Ciao, Carlangelo. Thank you for the talk. Sorry. I wanted to know when you talked about the second highest eigenvalue and so on of the transfer operator in the stationary case. That is something you can find out in the stationary case. Are there any results for the non-stationary case for the subsequent eigenvalues?
So this is a reasonable question, and unfortunately the answer is no, because this Hilbert matrix gives you an estimate of the gap. So I mean, this is kind of, but there is no second eigenvalue here. Right? There are no eigenvalue. So second eigenvalue normally gives you the speed of convergence, and that is exactly what this cone construction provides you. It gives you an estimate of the speed of convergence, but there is no way of knowing if it is optimal. Typically, it's not. It's a reasonably good estimate. The best one that, I mean, I know other tricks that can be used in order to prove this type of result, but typically they give the worst rate of convergence. Still, I mean, there is no reason why it should be optimal. And unfortunately, I do not know how to obtain an optimal rate of convergence. I think it's an open problem.
Thank you.
I mean, in general, maybe in some special case you can do something, but in general, it's an open problem. So.
No, there is no. Any other question?
Yes,